which is by Williams Surjanto, and the talk is going to be about finding fast flux traffic in DNS Haystack. Williams, it is over to you now, and you have about 25 minutes to speak, and this leaves us with about 5 minutes for questions. Thank you.
All right. Good morning, everyone. Can you hear me clearly?
Yes, very well. Thank you.
And how about the share screen that I just submitted? Is it?
Yes, it's also working absolutely fine.
Excellent.
Thank you.
All right. All right. So again, good morning, everyone, or should I say selamat pagi in Indonesia. So I hope you guys still in a good spirit after the first talk. And I'm very excited to be here, very happy, and to be honest, nervous at the same time, since this is my first ever research conference that I've attended. However, I will do my best to deliver the material as clear and concise as possible. But before we go into the main content and the details of the presentations, let me introduce myself first and my colleague very briefly. So yeah, my name is William Surjanto, and I'm here representing Indonesia Honeynet project, or you can call me Williams, that's okay. And my colleague here, also my teachers, Charles Lim, he is the head of cybersecurity lab in Swiss German University, and also full-time teachers and also researchers. All right, so now that the introduction is done, so today's topic that I would like to present to all of you guys, is finding fast flux in DNS Haystack. Okay, now I think the best way to open the presentation is to give is to start by addressing a very simple questions. What is fast flux? So if I want to explain fast flux, I will do it this way. So it's not like an expensive technique. Just consider it as a technique to evade detections. So it's used to evade detection from ISP by associating multiple IP address in a single domain name, and then constantly changing them in a quick manner. So the architectures can be depicted in the below figure in my presentations. So there are 3 nodes. The left side is the client. The middle part is the fastflux botnet. Additionally, I want to I want to inform you guys that fastflux usually use botnets to carry on their technique. And the right side is the command and control server. Now, how this works is similar to proxy. So every client networks on the left side is redirected by the fastflux botnets to the command and control server. And when the command and control server is done with all of the process, they will give the response back to the fastflux botnet again, and then the botnet will be redirected to the client. Now, these infrastructures give command and control server several advantages. One of them is anonymity. What I mean is that because every client connections is sent through the botnet. So the only thing that the client can see is the botnet, not the command and control server. So the command and control server is protected by the botnet. So we don't know how is the command and control server is actually working. How is it? How big is it? And what is the internal process in there? And yeah, that's the background of fastflux. And okay, cool. So what's make it so dangerous about fastflux? So in 2007 and 2012, mainly Fastlocks used for phishing incidents, so for doing scamming. However, throughout the years, for the last 8 years, Fastlocks has become used as an infrastructures for malware propagations. For example, in 2017, used as a proxy for Grand Cap ransomware, and it was concentrated in Romania and Bulgaria. So in conclusions, mainly Fastlocks used for hosting phishing websites and malware to attack critical infrastructures. Sorry. Okay, so I hope you got. I hope I got your attention by now of how important Fastlocks it is. So how do we stop this? I mean, how do we detect Fastlocks domain or Fastlocks networks? Throughout years of research, there are 3 techniques that a lot of researchers have used to detect Fastlocks network. Apologies, sorry. So the first one is active DNS probing, second is passive DNS probing, and the third is active service probing. Each one of the technique has its own advantages and has its own disadvantages. In this research that we have done, we use a passive DNS probing. So even though each of the technique have its own different approach, but in every research, they have they have the similar concept. So they gather enough DNS data using one of these technique and then analyze it either by statistic or machine learning, and they want to focus on a Fastlocks features. Okay. So how is the result of this research? I would say it's extraordinary. For example, a lot of previous research have come up with a brilliant idea of framework that could identify a Fastlocks domain. For example, Prodigy et al. So they create a machine learning model based on SVM for classifying Fastlocks domain and a benign domain. What I mean about benign domain is it's a normal domain that usually used by many people. And Anton Nakis, they create Notos reputation engine. Lombardo, they create Aramis framework, and Thomas et al. They have created hierarchical clustering to separate Fastlocks domain and benign domain. And last one is Kafuda et al. They actually use document fetch delays features to distinguish Fastlocks domain and benign domain, and etc. But hold on, but there is a catch here. In 2013, there is a research paper called New Trend in Fastlocks Network that have been released in Black Hat Conference. Now, in this research, there are 3 main things that highlighted by the researchers. So the big pictures first is that it turns out that the Fastlocks network has shifted for a couple of years. The first point is that the changing rate of the IP address and the name server addresses are slower than reported before. So most of the researchers, previous research know that using Fastlocks is actually they actually changing IP address, but it was in a very quick manner. They changing the IP address really fast. It's different with the normal domain. The second one is the shared and clustering IP address. So it means that several different Fastlocks domains that have been found actually indicating that they use shared IP address. So that means they're rotating different IP address in different domain address. Same IP address in different domain. So This actually gives us an indication that there is a well-established infrastructures model for a fast flux domain. And the third one, and it's also the problem that we're going to address in this research, is that fast flux network start look like a benign system. So for example, a benign system in this presentation is CDN. CDN is content delivery network. So this could be give us a lot of problem because there's going to a lot of false positive when we try to differentiate between benign domain and fast flux domain. So we got our problem. So we will start doing our research. So in this research that we have conducted, we separated into 4 stages. The first one is the collections. Data collection is like we just capturing all the DNS packet. As I mentioned earlier, we use passive DNS collection. So we put our device into the environment, and every transactions between client and the recursive name service in the DNS, we capture all of them. So a little bit of details of the environment is that we collected over 5 months inside an ISP infrastructures. It was located also in Indonesia that served around 1,000 enterprises and 3,000 residential users with a total bandwidth of 11 gigabyte plus, covering international and local traffic. And the result, we generally get 51 million raw DNS record. And again, this is still raw, still not processed. Okay, so as you guys notice that we got a lot of DNS data. If you want to check each of the DNS data, it will eventually causing us a lot of time. I mean, a very long time. So that's why we need to filter unnecessary data in order to move into another stage. So in this process, a pre-processing stages, we aim to filter a normal data. What I mean about normal data, it's like Google, Facebook, any domain that connected to advertisement, network time protocol server, and etc. So the framework is not overwhelmed with the captured data. So the result, we have apparently six major type of well-known domain. The first one is like, as you can see, is the well-known domains such as Google, Facebook, Twitter, TikTok, Instagram. All of them, we managed to filter all of them. And then there's CDN, a well-known CDN, like a Google CDN, Facebook CDN, NTP, root servers, antivirus, and the last one is advertisements. And then, okay, so we slimmed down our data sets. Now we got something that we can focus on. So the result of the previous stages, we will start to extract the DNS features that tie with the fast flux domain. For example, IP address change rate, TTL value. We also get the TTL value from the result, the ASN value, network locations, and so on. So this feature is actually used by the previous, this feature is actually used by previous research to detect fast flux domain. Now, after we extract each of the features from the dataset, it's time for the analysis. So we will continue the analysis to be analyzed for detecting fast flux domain. So we use k-means clustering to find a correlation of data in groups. So we want to have a very clear pictures of each of the groups. So we want to clearly define a line between fast flux domain and malicious domain. So from these stages, this gives us one bad news and one good news. Okay, we start to addressing the bad news first. The bad news is that the features that use in the previous research, in our testing, didn't help us enough to distinguish between those two domains. As you can see from the table above, there are no significant difference between these two domains. So we tried to do k-means clustering, and it was a mess. It was chaotic. And there's some benign domain go to the malicious domain, and malicious domain go to the benign domain. So it was mixed up. So we need to find another alternative to sort this mess. Yeah. And the good news is that because of that bad news, we found a new features that could help us differentiate these two domains. We come out with what's called web service contents. Web service content is very simple. It's basically just the size of the web element, like HTML, JS, and CSS returned by the domain. And you can get this value by using a simple Linux utility like wget, curl, or a Python library such as urllib2. So we found out that most of the Flux domain didn't return web service content in their top level domain. So for example, if there is a Flux domain called i.kazfv.com, so we go to the top level domain, which is the kzfv.com, then we probe the TLD to get the web service content. So that generally we do it, to get the web service contents. And the result is pretty good. I mean, at the top side of the table, you can see there is a benign domain always return something. They always return something of the web service content when we try to when we try to probe the top level domain. However, when we try to probe malicious domain, or should I say Flux domain, they don't return anything. They return zero bytes. So with this result, we actually get a more promising cluster result. From the analysis we do for k-means clustering, we got 3 groups of clusters. The top side is the clusters that use a very heavy a web HTML, and the middle side is the normal one, and the bottom one is the malicious domain. The quality of the clusters, we try to discuss the quality of clusters, and the quality of clusters, we use purity value to see how good the quality is the clusters, and the result see in the presentation is 0.92. And also additional finding is that we've also found that several Flux domain actually share IP to one another. So this is actually the same result that have been found in the 2013 research paper that I showed you earlier. So as you can see at the left side, the middle side, and the right side, so this is different Flux domain. And when we try to see the IP propagations, the IP rotation, they actually rotate the IP to one another. That's actually pretty interesting to find. So in conclusions, in this research, we have presented a case study of how Flux operate and can be detected in a very dense ISP network infrastructures. So during the experiment, we showed that utilizing web service content as one of the features for separating the malicious domain and the benign domain, it turned out pretty good. We got the purity value of 0.92. We got the result of purity value of 0.92. So for the future works, we want to reduce the, any miscalculations in the framework further. So we will try to extend to include the analysis that deal with the IP address propagations in the FastFlux network. So we could have more insight of how this FastFlux domain actually share and controlled by the command and control service. And also we want to extend the framework to include a larger data sets coming from multiple ISP or a higher tier ISP. So yeah, I think that's all. Thank you for your attention, and we will start moving on to the question sessions. Yeah.